So let's review what we have done so far so that we are on the same page, because this is the question of the Wheatstone bridge. Will be a question in the midterm for sure. So basically what we have our beam here connected, could be in any configuration. And then I will have one or more strain gauges. So let's say we have one strain gauge here. So how I approach this problem, the most important thing, I have to know this strain gauge is corresponding to which resistor. This is the first thing. So SG correspond to which R? Okay, R1, R2, R3, or R4. Or maybe we have multiple of them. So we need to know every single strain gauge correspond to which resistance. The second thing that you need to know is the SG resistance increases or decreases. In other words, is it R plus delta R or R minus delta R? So it depends on the type of the force. So for example, here, if I apply a force in this direction, this will be elongation. So R will increase. If I apply the force this way, so the beam will take this shape and SG will be expanding as well. So it will be R plus delta R. If the force applied in the other way around, which is this way or this way, compression forces or upward force, apply a compression force, so the SG will be compressed or R will be delta R. So this is all you need to know. Identify which R, and is it R plus delta R and R minus delta R, and then substitute in this formula. We always assume that all the resistors are equal to each other. So then this everything will becomes an R, and one or more of those resistors will be an R delta R or an R minus delta R. That's all. This is how you approach this question. Then it becomes very, very straightforward. Again, I'd like to apologize for this noise that you're hearing whenever someone log in or log out. I don't know what happened. Someone, for some reason, I don't know, the whole reservation was wiped out. I have to redo it again, but then I have to go to certain places so that I can edit and I can do the changes so that I need to change the setting, because the setting default is that whenever anyone log in or out, there is a sound. So I need to do that. I will do it after the class. So hopefully tomorrow you will not hear this annoying sound. Okay. Now let's go for, we have 4 strain gauges. Not just one. We have 4 strain gauges. So let's go back to the formula that we have here. So your V out is equal to our Vs. And as you can hear, this is the formula. And you have to look to the configuration of the Wheatstone bridge. R3 times R2, R3 times R2 minus R1 times R4 divided by the summation of the resistors of each leg. Okay, so R3 times R2, so this would becomes R3 R2 minus R1 R4 divided by R3 plus R4 times R1 plus R2. Why I'm saying this? Because if I change the numbering here, you have to make sure that you are following. It's not just, I mean, these numbers because of the order of the resistors. So if I change the order of the resistor, you have to make sure that you are changing the formula accordingly. Okay, now here everything is equal to R, so this formula will becomes everything in R. And now let's see here. I apply the force this way, so the strain gauge 2 and 3 will be, so the beam will go like this, So R2 and our string gauge 2 and 3 will be elongating. So for R2 and R3, it will be R plus delta R. And for the one that at the bottom here, it will be the other way. It will be R minus delta R. So now it becomes a very simple substitution problem. That's all. So R3 becomes R plus delta R times R2, which is R plus delta R, minus R1, R minus delta R, times R minus delta R, divided by R3 plus R4, R3 in top, R4 is in bottom, so this becomes R plus delta R plus R minus delta R. And same thing here, R1 and R2, one on top, one on bottom, so R plus delta R plus R minus delta R. So, and there is of course Vs multiplied here, which is this input voltage, which is also will be given to you. So this becomes R square plus 2 delta R times R plus delta R square minus, sorry, minus here, R square minus 2 delta R R plus delta R square divided by, this will cancel, so we have here 2R times 2R. So R square will cancel with R square, delta R square will cancel with delta R square. So we have 4 delta R times R divided by 4 R square. R with the square will cancel, the 4 will cancel, so we'll get delta R over R. So as you can see here, compared to the previous case where we have delta R over 2R, now we have delta R over R, so this will give me more voltage, which is what I want. I want to have more voltage induced. This can help me to measure better the change in the resistance. Okay. This solution, you have it here. The full solution is done by Molly. He was a student in one of my classes, and I just put her name here with her ID to thank her for this nice solution for this problem. Let me see before I move forward if there's any question. Our history prof had a similar problem during fall term. Okay, I forgot how she managed to solve it. Okay, I think I can. I will try to fix this problem once we are done with our class. Okay, now load cells. This is another type of sensor that we will have, and I will show you some of the one load cell that I have. There is here some nice YouTube links. I encourage you to go and watch them about load cells and their uses. So what is a load cell? It's a transducer, or it's a sensor used to convert a force into electrical signal. Again, this is the wide definition of a sensor. What is a sensor? A sensor changes a physical quantity into an electrical quantity. So here, the physical quantity that we want to change is the force. And this conversion from a force into electrical is done in 2 stages. The first thing is there is some mechanical arrangement to be able to sense the applied force, and with certain mechanism will be applied to deform the strain gauge. Okay, so the force that you apply will be applied to a strain gauge, and that strain gauge will be deformed. Once that deformed with the help of the Wheatstone bridge, this deformation in the strain gauge, either in elongation or in compression, will be converted into an electrical signal. Let me show you this. Hopefully it is working after, because this has been why long time not working. Okay. Okay, so this is a load cell. Okay, so this load cell here, we apply the force at the bottom here. Okay, so I can apply a compression force, and you can see here the reading, or I can apply tension force, and you can see here it gives you the force there in newtons that I'm applying. And also it tells you, I'm not sure if you can see that or not, to the far right, it will tell you if it is tension force or compression force. And last time we mentioned something like this. We said that with the strain gauge, I will get a voltage that is positive or that is negative. So the strain gauge can help me, the Wheatstone bridge can help me to decide or to tell the direction of the force that I am applying. Now, the voltage that we get, and we have seen in the previous examples, in the range of the millivolt. And this is a problem here. Why? Because when you have a voltage very small in the millivolt, sometimes you have noise around you. Sometimes the noise is even more than this voltage. So you need to get this signal amplified. And this is what we will be studying later on using the amplifier. And we will see next week when we talk about temperature sensors. Again, the voltage that we are getting is very small, in microvolt even, and this makes it very challenging for any device to measure it, not just because of the noise but also because of the device sensitivity. You have to have a very sensitive device to be able to measure these voltages. Alternatively, what we can do, we can use an amplifier. The amplifier will amplify the voltage, make it in the volt range, becomes much easier for us to measure it. Now, again, this is a voltage. We need to convert this back into force, because yes, the transducer will change this force into a voltage, but I'm not interested in the voltage. I am interested to know how much force was applied. So I have to go back and I have to find the force. And there is usually what we call calibration curve. Some curve like this will give you in one axis, for example, the volt, the other axis the force, and some curve like this. Then you have to enter this algorithm to convert what volt you measure into the force that you are interested in. Now, the load cells have different types based on the loading uh, direction. For example, the one on the far left is called tension. We can apply only tension force on it. We cannot apply compression forces. And this one, on the other hand, is compression type load cell. This one is alternating. This is like the one I showed to you here. This one, I can apply compression forces and I can apply tension forces. It works for both, but not every load cell can be worked as both. Some of them can be only for tension, and some of them they are only for compression. This is for bending or cantilever forces. So you apply the force in this direction or in this direction, and your load cell is connected to one side permanently. So you're applying a sort of cantilever force on the load cell. Now, let's see here something very interesting. Last time when I told you what will happen if I have one strain gauge here, we call it 1, another strain gauge here, call it 2, and I apply a force in this direction, then this will be elongating, this will be elongating. How about if I have all the 4 here? Now, it doesn't really matter what numbering you will have, because all of them will have elongation forces. And if this is the case, then I will get 0 voltage, because I always, you notice now, always we wanted that some of the strain gauge will give me R plus delta R, and some will give me R minus delta R, because the formula that we have, V out is equal to Vs times R2, R3 minus R1, R4. So if the changes will be the same in all the resistors, this will be cancelled and you will get 0. And we don't want that. Why? Because we want, when we apply a force, I should get a voltage. Here, I will not be able to get a voltage. Okay, so how we can overcome this problem? By changing the orientation of the strain gauge. So here we have 2 strain gauges perpendicular to each other. One in this direction, the other in this direction. So this is going in this direction and this is going in that direction. And here there is no force applied. So when apply a tension force, what will happen to this strain gauge? It will be elongated, but this strain gauge will be compressed. So having tension force, you will see that this one will have an increase in the R, in the resistance, and the other one will have a decrease in the resistance. And that's, many times, this is what exactly you wanted. Now, on the other hand, when I apply compression forces like this one, the opposite will happen. And that's also what you want. You want each strain gauge to act completely opposite if you change the direction of the force. So here, the one in the top, when you apply a compression force, will be compressed, but this one will be elongated. And you will have completely opposite effect on the resistance, and that can help to solve the problem we just mentioned last time. So let's look here uh, what is happening inside the load cell. So this is a load cell that have, or we apply tension forces on it. So here we have the arrangement as such. So here it is R1, R2, R3, and R4. Now you can see here there is R1 here, and in the other side or opposite to it is R3, and here is R2 and R4. And when we apply a force, a tension force to it, this object or this load cell will start to elongate, which will lead that the strain gauge 1 will start to elongate because the force is in the same direction as the strain gauge. So this will start to elongate. So for this, R will increase. On the other hand, the force here is perpendicular to the strain gauge, so this will start to be compressed. So for this one, R will start to decrease. So yes, I'm applying a tension force, but you will have some strain gauges will be affected in a positive way, meaning the R will increase, the others will decrease, then you will have a voltage coming out of this. This is a cantilever beam. Now, if you notice here in this and this, we have the 4 strain gauges. We use all the 4 of them. We don't use 1 or 2, but use the 4 of them. Why is that? Because again, this gives me more voltage. So I'm changing the stress or the strain into a change in the voltage. I want to maximize this. Okay, so to maximize this, as we have seen for 1, for 2, and for 4, when we have 4, we get the maximum voltage. So I want to have all of them connected. So here we have 1 and 3 on top, 2 and 4 at the bottom. And this is how this is a cantilever type of strain gauge. So we connect it permanently from one side, apply the force from the other side. So for example, here we connect it here. It will be like plugged using some certain bolts, and then We apply the force. So these two, if the force is going from up to down, these two will increase, the R will increase, and the bottom, the R will decrease, and vice versa. If the force is in this direction, we will have the opposite effect on the strain gauges. And here is the circuit, and this is explains what I just mentioned. Now, how the strain gauges look like physically, we have different types of, sorry, the load cells, how they look like. Again, a load cell is nothing but arrangement of strain gauges. That's what is a load cell is. Okay, so we have, if you can look here, if you look carefully here, this is the Wheatstone bridge. So inside here there is an arrangement of Wheatstone bridge. Before I move forward, there is a question here. Let me see it. Can you re-explain how we know if the strain gauge is elongated or compressed? Okay, I would rather go back here. This one. This is the most important one that you can see. If the force that is applied as a tension or a compression, you use this one. So you see the direction of the strain gauge. If the force, tension force, is in the same direction, because the strain gauge is nothing but like this. It's a wire actually. So I'm applying the force in the same direction as this. So actually I am elongating it. So the R will increase. Why the R will increase? Because R is equal to rho L over A. So when I elongate the wires, L will increase. And when I elongate a wire, A will decrease. So R will increase. So this is why this is will increase. If my strain gauge was placed 90-degree with the force, when you try to pull it, remember this is how it looks when there is no force. So when I apply the force, this will be compressed. So L will decrease, A will increase, and then R will decrease. And vice versa when we have a compression force. Now, in the previous example, when we have a force in this direction, for example, when we have a cantilever force, you will see here this, when we apply the force in this will becomes like this. So the one in top will be elongating, the one at the bottom will be compressed, and then the one on top will increase the R, and the one at the bottom will have a decrease in the R. Hopefully that explain what is happening. Now here we have different shapes of strain gauges. For example, this strain gauge, call it the S type. This S type is used for basically mainly for tension forces. So you apply a force from this one and start to pull. So this is a tension force. This one and this is washer type. This is a compression force. When you want to apply a compression, there is no tension force. You can't apply tension force here. So for example, this one, if you place an object on top of this will be compressed down, and then you'll get the signal from here, which correspond to the voltage. Now, let's see some practical applications of the load cell, something that we see in our life, and let's to appreciate more the load cell. This is something familiar to us, which is basically the balance or the way that we use it in the kitchen. Okay, so this is scale, a kitchen scale, small one. Okay, and of course in a scale, what type of force you will apply? It is always compression. You will never apply tension force here, because basically you put your object here on top of the balance, so it is always a compression force. So what is inside this? Again, if you look here, this is the load cell, and this is a compression type of load cell, and you can see here there are 4 wires coming out of it. These 4 wires are nothing but the 4 wires that comes from the Wheatstone bridge. So this is your Wheatstone. You will have these 4 wires coming from the Wheatstone bridge. This is So inside there is a Wheatstone bridge. Now this will be taken, this is a microcontroller similar to the one that you have. It will measure the voltage that you have there, and it will apply the DC voltage. So in two terminals, you will measure the voltage. From the other two terminals, you apply the voltage, and everything is applied here. And then you will have sort of calibration to calibrate this amount of weight, because the results are in voltage. You have to calibrate this to give us the, this is in ounce or in pound or in gram or any type of measurement. Okay, and we have a little bit of programming here to change the scale. When you change the scale or you change the unit from the British to the SI unit, basically you are changing the code. There is a simple code that is written in C++, similar to the one that you used in your microcontroller to do this conversion. So you select, you do when you press a button here, basically you are changing the code. That's all you are using. Another example here, this is used in airports, basically to where your luggage is. So basically, again, this is here it is. This is the load cell inside. So this whole balance, when you open it, is nothing but a load cell. And this load cell will have now what type of force? This is only tension force. You cannot apply with this a compression force. So this is why some load cells, they are only compression, some of them they are only tension, some of them are both, depends on the application. So for this one, I don't have to have a load cell that can sense both tension and compression, because the type of force I will be applying here is only tension forces. So here, if you, as I said, if you just open this, you see here a screen, digital screen, call it LED. This is basically, or LCD. You will have something like this in your kit, and easily can be programmed to show the readings as numbers. But as again, there should be some code to do a conversion between the voltage that you are making and, or you are measuring, and the actual forces that is applied. Okay, very good. So this is the load cell. What, there are two important things about the load cells, which is the, or the sensitivity of the load cell. What is a sensitivity of the load cell? It is MV per V. What is MV by V? Remember, we said that in the strain gauge arrangement, when we have a Wheatstone bridge, there is a voltage Vs we apply. Okay, so here the sensitivity, it will show you how much maximum full scale voltage in millivolt I can get per the excitation voltage. So for example, if we have, these are the standard sensitivities, 2 millivolt per volt or 3 millivolt per volt. Let's see how we calculate this figure. For example, if a load cell has 10 volt excitation, it means that your Vs that you connected to the strain gauge Wheatstone bridge arrangement is equal to 10 volt. And when you apply the maximum voltage, you are getting, or sorry, the maximum stress, you are getting 20 millivolts. So this is your full scale output. This is for, because you know, for every scale, for every load cell, there is maximum force you can apply. If you exceed this, you will damage the load cell. This is why when you buy a scale in the kitchen, they will tell you this is maximum 5 kg. If you try to put more than 5 kg, it will not show you anything the scale. It will be out of scale. And if you keep doing this, adding more than the capacity of the scale, you will damage the load cell. So the maximum capacity or the full scale here is 20 millivolt. So just divide the 20 by the 10, you will get 2 millivolt by volt. And this is what is called the sensitivity of your load cell. Now, strain gauge and load cell, what they are basically, they are resistive sensor. What do we mean by resistive sensor? It means the following: we are changing the physical phenomena to change into resistance. Now, this is basically how the strain gauge works and how the load cell works. However, we change the change in the resistance into change into voltage using the Wheatstone bridge. So we are doing an extra step here. But the strain gauge itself is a resistive sensor. It's a sensor that when you apply a force to it, its resistance will be changing. So this called resistive sensors. Okay. There's a question here. Let me see. Does that say resistance? Resistive sensor. This is an adjective. Resistive sensor. Let's see other types of. There's something. Let me just see the questions exactly. No, the written piece you wrote above. Resistive. This is the physical phenomena, which is could be force in this case. Is change it converted into change into resistance, and this change into resistance we convert it to change into voltage. Okay, now let's see that this what is a displacement sensor. So this is another type of resistive sensors. Displacement by itself is a vector quantity. Okay, so you need to have a magnitude and direction for it, for the displacement. Now this will represent a change in a position. Your object was in certain position and then moved to another position with respect to certain reference. Now we use this to measure different things: force, stress, pressure, and velocity. So the displacement sensor is used widely by mechatronics engineers, mechanical engineers, as well as civil engineers. For us, we are more interested into the stress, how to convert this into a stress. How they look like. The This is the resistive transducer here, and there are two different types. When you apply a force, linear force, okay, so basically you connect your force uh, to this rod, and then you can increase, you can apply force in this direction or in that direction. Now what is basically this? This is a slider actually, and you will apply here a certain voltage called Vs, and when you apply the force in this direction, the slider goes up. If you apply the force in the other direction, the force will go down. So what I am measuring here, I'm measuring another voltage. When you look carefully to this is basically a voltage divider. So this is your Vs, and this is the voltage that, so if this is your R1 and this is your R2, so your V out is nothing but Vs times R2 divided by R1 plus R2, which is R, which is the total resistance here. So now, when this goes up, R2 will increase, so V out will increase. So again here, the force is converted to a change into resistance that is converted to change into a voltage. And then you have to do the calibration so that you will know how much force has been applied. Or if your force is rotational, we have exactly the same thing, but the slider now will rotate. Instead of going to a linear motion, it will go to a rotational motion, but it's exactly the same thing. We have Vs, which is this, we have the slider, and we have V out. So if we go in this direction, the slider going this, you are reducing the R, so you get less voltage. If you go to this direction, you are increasing R, which is from here to the point of the slider, then you are increasing the voltage. So you can apply to this two different types of forces. It depends on your application. Another important sensor, especially for environmental engineers, which is the soil moisture sensor. Now, these sensors are used to measure the water content in a soil. So if you have a certain garden or you have farm and you want to control how much water to give, as you know, we have scarcity of resources. Uh, we don't want just to throw water and that's it. We want to control the amount of water that we use it for the to irrigate the plants that we have. So we need to know, we need to have an idea before we turn the water on. Is the soil dry or it is wet? If it is wet, how much wet it is, and then we can arrange the irrigation period so that we optimize our resources and we don't just throw the water like this. And how to do that, how to tell when to start the irrigation is by using this type of sensor, which is here resistive sensor or soil moisture sensor. How it works: basically the sensor consists of two probes that will measure the volumetric content of water. Okay, now we apply voltage between these two probes, and hence when you apply a voltage, so basically you have two probes like this. You insert them into the soil and you apply a voltage here. When you apply a voltage, a current will start to flow. But between the tips of these two probes, there is a moisture. Now, if the moisture has a lot of H2O, a lot of water, water is a good conductive of electricity, then you will have a high current, or the resistivity of the soil is low. If the soil is dry, on the other hand, there is not much of ions to let the current flow here. So you have a very, very small current that is going through. And this small current is a reflection that there is no water or the soil is dry. So this is how the resistive sensor can be used to measure. And this is just some examples here. This is a soil with a lot of water, and this is soil dry, and this is like a very simple circuit. This is your sensor that you just put it here, the moisture sensor, and they are using the same Arduino kit that you have, and this LCD to show you the is this is if the soil is moisture or dry, using this simple technology. Okay, so with this, let me stop the recording. We are done with our lecture today.